Okay, I'll have information about the exam Tuesday. I haven't run the numbers yet. I can promise you the average will be lower. I just don't know how much lower. It always is, but we'll see the exact results when I get to it. And if anybody wants to go over the results of their exam with me, please find me during regular office hours or some other time if those don't work for you. All right, but what we're going to continue on today is we're going to finish chapter 7, which is all about energy-related things. So energy, heat, enthalpy, all that stuff. And we're going to transition into chapter 8, the very beginning parts. All right, so the last sort of numerical thing we need to go over for, hang on one second. That was a little bit live. All right, the last sort of numerical thing we need to go over is another way to calculate delta H. I think in your notes that I posted, it might be labeled as delta E, but really, again, delta E, delta H kind of used interchangeably, so don't freak out about that in most contexts. They're kind of done the same. And what we're going to cover is a method of using bond energies to calculate the delta H for a reaction. So way back in probably chapter 3, we introduced what a bond energy is. So that's when you have two atoms bonded together in the gas phase, and you break that bond to separate the two. And we called it delta E at that point, because we hadn't talked about energy and enthalpy yet, but really it's a delta H. It's a change in enthalpy, and that change in enthalpy is called the bond energy or the bond dissociation energy, or technically BDE as we abbreviated before. So that's what that refers to. We learned that back in chapter 3. We didn't do a lot of numerical things with it, but we learned how to compare bond energies and the factors that control it. Now, if we have the actual bond energy values that are involved in the chemical reaction, we can use them also as another way to calculate delta H. It's kind of similar to what we did last time. Last time we finished up with using enthalpy of formation, delta H of formation, to calculate delta H for a reaction, products minus reactants. We can also do the same thing with bond energy. The only difference here, and the part that gets a little bit confusing at times, is that it's not going to be products minus reactants, it's going to be reactants minus products, because bond energy is defined as the energy it takes to break a bond. So we're breaking bonds on the reactant side, forming them on the product side, and so we need to do in the opposite order. And let's talk a little bit about that process then. So basically the way we're thinking about this is not really how chemical reactions work, but again, because we're calculating a delta H, which all that matters for delta H is the final and initial states, not how we got there. The way we're kind of imagining this happening when we use bond energies is we're going to take the reactant molecules and we're going to break all the bonds in those molecules first. We're going to calculate how much energy that takes. So that's going to require energy inputs. To break a bond, it's always going to be a positive delta H. You have to put energy or heat into it to break the bond. So we're going to break all the bonds in the reactants. They're going to basically we're just going to atomize the reactant side if you want to think about it that way. And then on the product side, those atoms are all going to scramble up and they're going to form new bonds on the product side. And so then we're going to sum all of those up. Now the only difference though is because on the product side we're forming bond, the energy is going to be released. That's going to be an exothermic process, which is why we subtract it from the reactant side. So a different quantity of energy and a negative quantity is going to be involved when we form the bonds. So when we form the bonds on the product side, that part is going to have a negative enthalpy change. As all those atoms that we broke up on the reactant side form all the new bonds that are present on the product side. And so then what you end up with is delta H is going to be, again, a similar equation as last time for delta H formation, but in the opposite order. It's going to be the sum of all the bond dissociation energies on the reactant side minus the sum of all the bond dissociation energies on the product side. So again, it's reactants minus products. Delta H formation is products minus reactant. Try to drill that in your head as soon as possible. And again, sigma here means sum. We're adding them all together on each side. And as we defined above, BDE, or sometimes just BE, you'll leave the D out, is bond association energy, which are going to be typically given to you in problems like this. Another difference, as we'll see, we're going to just do one example problem. They're a little bit tedious, so we're not going to do a ton of these. The other difference is that when you're using bond association energies, unless it's a diatomic molecule, it's not going to just have one bond association energy for that molecule. You have to add up all the individual bonds that are in that molecule. It's not going to be just one value for the whole compound unless it's just a single bond between the two. So you have to make sure you account for all the different bonds that you have on the reactant side and all the different bonds you have on the product side, which in many cases the molecules will have more than one bond. And it's also important to account for bond order because, as we talked about in chapter 3, the bond order is going to depend, that's going to be a strong determinant of what the bond energy is. So if we give you a reactant O2, you need to know that that's a double bond because that's the correct value of the bond association energy you're going to use for that, not the single bond value, which would be much smaller. All right, but we'll get into that here. So we're going to do this one here as an example. And honestly, this type of problem is really like testing your accounting skills more than your chemistry skills, to be honest. It's just tabulating all the bond energies on one side, tabulating all the bond energy on the other side, adding them together, and then subtracting the two totals from each other. So it's more like an accounting exercise than chemistry. So we have this reaction here. This molecule is called formaldehyde. You've probably heard of that before. It reacts with phosphine, which is horribly toxic, by the way, and you basically get this more complicated product here. So what we're going to do then is on each side of the equation, we're going to sum up all of the bond energy values. So all these different bond energies are given. And as you'll see, you notice once again that there's different values for carbon-oxygen double bond, carbon-oxygen single bond. So every time we're tabulating a bond energy, we have to make sure we're using the correct one that corresponds to the bond order that substance actually has. Here they're all sort of clearly spelled out for you for the most part, but sometimes you'll have to make sure you're aware of what the correct bond order is if it's just given to you as like O2 or N2 and so on. All right, but on the reaction side, what we're going to have is we're going to start with, and we can do this in any order, but if we look at this first reactant here, it has two CH bonds. Remember, we're not going to just use CH bond energy once because there's two of them. There's one CH bond there, one CH bond there. So we have to add up two of those. So we're going to multiply that by 2, the CH bond energy, which is 413. These are all kilojoules per mole. So 413 kilojoules, 826 kilojoules for the CH bonds. And then this first reactant also has a CO double bond. So again, there's not going to be just one number for each reactant and product necessarily. It's going to be one for each bond that has. So here we also have a C double bond O in the first reactant. So we need to add that in. There's just one of those. We don't have to multiply by factor, but that's going to be 745, the correct number that we would use for a double bond. And then we also have this thing here, pH3, which we didn't have the detailed Lewis structure of. Pretty obviously, it's going to just have 3 pH bonds. You can't have hydrogen as a centroatom, so it's just going to be phosphorus with 3 hydrogens around it. So we're going to have 3 pH bonds. It'll just be this. No other way to draw that reasonably. So 3 pH bonds for pH3, so we're going to have to add those up as well on the reactant side. So the pH bond enthalpy is 320 kilojoules per mole, and there's 3 of them, so we're going to multiply by 3. That gives us 960. So on the reactant side, we add all of those together. Those 3 numbers added together is 2,531. All right, so that's the reactant side. Now we need more space for work because, as I said, these problems are kind of tedious. So blank page here to start on the product side now. We're going to do the same thing on the product side. I'm going to flip back and forth, unfortunately. But anyway, on the product side, we look here. Only one product, but a bunch of different bonds that we have to account for. So we have still 2 CH bonds in this product, one there and one there. That and that didn't change, but there's still 2 of them, so you have to account for them on the product side. So it's numerically the same as what we had on the reactant side for those CH bonds. And then in whatever order we want to go in, we have also now a CO bond, but it's no longer a double bond, it's now a single bond. So you have to use the correct value for CO single bond. There's one of those in the product, and the value for single bond is 358. So that's 358 kilojoules. And then we have an OH here. That is a new bond that's formed on the product side. So we have one OH. And the value for OH is 467. Another difference between this and delta H formation is there is no bond energy value that you can just know off the top of your head. With delta H formation, all elements are zero, as we talked about. For these, you have to know all the numbers. There's no shortcuts to any of them. And then we have one carbon phosphorus single bond in the product, so that's another new bond here, carbon phosphorus single bond, which is 264. All these bond energy values have to be given to you, as we said. So you just have to look through the problem to find the right ones. And then we have now 2 phosphorus hydrogen bonds. We had 3 in the reactant side, we still have 2 left on the product, so we're going to account for those as well. pH, there's 2 of them, that value is 320. So from the pH bonds, we get a total of 640. All right, so all those numbers added together gives us the sum on the product side. Which comes out to 2555. All right, and then finally to get delta H, it's going to be reactants minus products when we're using this approach. So it's going to be that sum that we got for the reactant side up above minus the sum for the product side that we just found. So for the reactant side, we got 2,531 kilojoules. For the product side, we just got 2,555. And when we subtract those, we get negative 24 kilojoules. So this will be overall an exothermic reaction. All right, so that's, again, there's a lot of accounting that goes into this, a lot of number crunching, but it's not terribly difficult. You just have to make sure to carefully avoid potential mistakes as you tabulate things and make sure you're using the right bond energy values for everything. All right, any questions on that? Yeah.
Did you say it was
Exothermic. Yeah, it's negative. If I said endothermic, I misspoke, but it is exothermic. All right, any other questions? Okay, so that's the last sort of numerical problem from Chapter 7, the last type that we'll have to do. The last thing we're going to cover, which your book doesn't do this a lot, especially in the first half of the book, but in Chapter 7 and a little bit in Chapter 8 they do, sort of talking about the societal importance of what we're learning, which maybe sometimes you wonder about yourself, like why do I care about this topic? Hopefully you find it interesting on its own, but you may think, well, what good does it do me to know delta H and how to calculate it and all that stuff? Now, the importance of the stuff we learned in this chapter is all relevant to fuels. So we live in Houston, so we all know about the energy economy, oil and gas being a very common or very big part of that. So let's talk a little bit about fuels and kind of how it relates to enthalpy, the stuff we learned in this chapter. So we're not going to spend a ton of time on this, but just to give you the sort of highlights, the things we kind of expect you to be familiar with. So a fuel, what's the precise chemistry definition? It's a substance that has a lot of stored energy. And so what that means is we release that energy in some way to then usually do work with that stored energy. And normally we release it by burning the fuel. There's also things you may have heard of called fuel cells, which are devices that directly convert fuel stored energy into electricity. So that's another way, but not as common, is just burning it. So you burn it and you release a ton of energy. As you know, when you burn something, you get most of that in the form of heat. So the most prominent component of our energy economy are all the fuels that we use. So this is, again, we need ways to store energy. And we need ways to transport it, and that's where fuels come into play. And the most typical fuels that we use are all called fossil fuels. So these are ones that are formed by the decomposition of living organisms over millions of years. And so most fuels that we use today, we have a gas-powered car, diesel, jet fuel, all those come from fossil fuels. Coal, which we still use, natural gas, all those are classified as fossil fuels on some level. So those are the most common sources of fuels that we have. They're just different sources that come from living organisms that decomposed, usually under very harsh conditions. So, you dig them up from the ground where there's really high pressure, sometimes really high temperatures under there, and it forms these energy-dense substances that we can then dig out, process, and use. So let's talk about the two main types of fossil fuels. And obviously in Houston we have a big economy that's built around this. So one of those is petroleum. So petroleum is mostly made up of hydrocarbons. Now in reality, petroleum is a really complex mixture of substances, and depending on where you get it from, it's going to be somewhat different in composition. But the major components are all hydrocarbons, which have the general formula CXHY. The hydrocarbon means a substance that only has carbon and hydrogen in it. Now, the different types of fuels that we get from petroleum sources, as we'll talk about, they're mostly liquid. So petroleum itself is a liquid, and then most of the things that we separate and use out from that are also liquids. And they're separated into different components that we use as fuels. And those are things you've heard of: gasoline, diesel fuel, jet fuel. Those are the main fuels, but there's also many other chemicals that come out of this that we use for preparing the substances that we use in our everyday life. So a lot of plastics come from initially petroleum sources, the precursors to make those plastics more precisely. And so the difference between these different things, what's the difference between gasoline, diesel, and jet fuel? Well, those themselves are still mixtures. They're not pure substances either. But basically, the sort of average number of carbon atoms in the molecule dictates whether it's going to be classified as gasoline, diesel, or jet fuel. So I don't remember these numbers exactly. I haven't worked on fuels in a long time. But gasoline is, on average, around 8 carbon atoms. So you've heard of octane that we talked about last time. It's a major component. And gasoline has 8 carbon atoms in the chain. Diesel is a little bit heavier, so usually like 10 to 12. And then jet fuel is probably even heavier than that. So those are more carbon atoms in the chain. So those are the differences between gasoline, diesel, and jet fuel. And they're all separated out from crude oil, petroleum, that we dig out of the ground. Now, the other major type of fossil fuel is coal. Coal is mostly carbon, doesn't have a lot of other things in it, and it's solid. So little briquettes, almost like a rock, but it's very soft. And depending on where you get the coal from, it's going to have variable carbon content. So the percentage of carbon by mass in coal is going to vary from source to source. Now, your book gives you all these different, there's 4 at least of different, types of coal, like anthracite, and I think bismutite is one of them. All these different proper names, geological names for the different types of coal. We don't want you to know those details, but you should be familiar with the concept that all those different types of coal have different carbon percentages in them. And the reason that that's important is because the higher carbon percentage that you have, that's going to mean you have more stored energy in that coal. So the most energy dense, form of coal will be one that has the highest percentage of carbon in it, the one that would then release the most energy when you burn it. And the reason for that is because when you burn coal, what you're mostly doing is you're just combusting carbon to make CO2. And this is the really, exothermic one that has a huge negative delta H associated with it. And the more carbon you have, the more energy you get out. Because other parts of coal would already be partially oxidized. So when those would still burn to CO2, but they would then release less energy because they're already sort of partially converted to CO2 already. So that's why the more carbon you have, the more stored energy. Now, as you are also aware, if you follow the daily news, there are concerns about our continued use of fossil fuels. And this is not a geology or atmospheric science or climate science class, so I'm not going to go into all the details of that, and I certainly don't want to stir up a political discussion here, but you've probably heard of all these things in either a scientific, political context, or both, and the major concern about fossil fuels stems from the greenhouse gases that they release. So when you burn a fuel, you release water vapor, which is a greenhouse gas. The process of, you don't release this when you burn it, but the process of bringing up petroleum from the ground or other, fossil fuel processes sometimes releases methane. Also, farming releases a lot of methane, something we've probably heard of. And then the big one from burning fuels is carbon dioxide, CO2. Those are all classified as greenhouse gases, and CO2 is the one that gets the most attention. And they basically trap heat, which leads to the concerns then that they would keep the Earth's surface warm, sort of disrupt the natural temperature regulation that the Earth has. And so then that leads to the concern that if you increase the greenhouse gas composition of the atmosphere, if you burn a lot of fuels and put a bunch of CO2 up there, for example, that increased CO2 may warm the Earth unnaturally, and then there's obviously environmental concerns associated with that. So that's the major concern about greenhouse gases and the reason why there's been this push to move away from fossil fuels. Now, the other concern about fossil fuels, which is not something that we're going to have to deal with in our lifetime, but is ideally before the world ends, is going to be something that is a problem, is the long-term viability. So fossil fuels won't last forever. As I said, they take millions of years to form, and we're using them at a much faster rate than that. Really the fossil fuel economy didn't start until probably at least maybe 200 or 300 years ago at the most, where it became really common to burn fossil fuels. And so, in that time scale, we've burned a lot of them off. We've depleted the reserves to some extent, and they won't last forever. Now, we keep sort of revising the estimate for when this is going to be a problem, but they do take millions of years to replenish. So at some point, if we've exhausted our supply of fossil fuels in the Earth, they're not going to replenish fast enough for us, not even close. So we have to come up with alternatives for that. We find, there's always new sources of fossil fuels that are discovered, new ways of getting them out of the ground. So there is technology that has kind of, prolonged the viability of fossil fuels in the near term. But at some point, I don't know if it's hundreds of years or more than that down the road, but at some point before the world ends, there's going to be likely a shortage of those fossil fuel sources, so we need other ways of storing our energy and of preparing fuels. So then that sort of leads us into the last part of this, which is what are some possible energy sources for the future? There's a lot of considerations that go into deciding, well, okay, if we can't use petroleum and coal anymore, what should we use instead? And there's a lot of factors that go into that, cost being of course a big one, but other chemistry related things on top of that. So one is, that's talked about a lot, is hydrogen as a sort of, fuel for the future. So one advantage of hydrogen is that it has a very high energy density. So when you're thinking about, using a fuel, you want it to store a lot of energy, pack a lot of punch. If you wanted to replace gasoline with something that was much less energy dense, well, you'd have to fill up your tank a lot more often, or you have to carry around a lot more gasoline with you to get the same range. So you need to make sure the energy density makes sense for what you're using it for. So hydrogen, in terms of weight, is exceptionally good for that, because hydrogen H2 is the lightest gas that we have on Earth, and when you burn it with oxygen, you release a lot of energy. So if you do the combustion of hydrogen, all in the gas phase, your delta H for this is minus 286 kilojoules. That's a lot of energy for something that has a mass of 2 grams per mole. H2 is basically molar mass of 2 grams per mole. So you're releasing a lot of energy. So that's great. The problem, though, with hydrogen is there's 2 main problems. The other great thing about it, though, that is sort of obvious from the combustion reaction, is that you only produce water as a product. So you're not producing, CO2, or there's when you burn coal especially, there's other like harmful, sulfur containing and nitrogen containing gases as well. So it just produces water. It's very clean burning, and ideally, if you can come up with the right technology to do this, you would be able to then take the water and put energy back into it to get back to hydrogen. So you could have this sort of closed loop fuel cycle. That would be great. The reason that doesn't happen a lot right now, or at least not on a large scale, is that hydrogen is expensive to produce. Let me check something real quick. Someone's calling me, and I hope it's not important. No, I have no idea what number that is. All right. So hydrogen is expensive to produce, particularly from water. The cheapest method to produce hydrogen now still uses methane as sort of the input. So you're still using a fossil fuel to make most hydrogen that we use today. So this, you can split water into hydrogen. If you guys ever put a 9-volt battery into salt water, you know that. But it's not very cost effective to do it that way, and not very energy efficient either. And the other problem with hydrogen, even if you can make it perfectly well, is that it's difficult to store and transport. It's a gas. Most of the fuels that we use, especially for transportation, are liquids. And because it's a gas, in order to get good volumetric density, you have to compress it to really high pressure. We're going to talk more about gases in chapter 8, so that'll start to make more sense. But you have to compress hydrogen a lot, often to unsafe levels, to be able to get it to compete effectively with liquid fuels that we commonly use. So there's difficulty of storage and transportation of hydrogen. It's extremely explosive. If you've heard of the Hindenburg disaster from World War II era, that was a ill-fated hydrogen balloon that blew up because, again, hydrogen is difficult to control in that way. So there's a lot of problems with hydrogen, but if we could get it to work, it would be a pretty sweet deal for us to be able to just use hydrogen, burn it to make water, and get it back to store the energy that we need. Another concept that's being developed a lot are called biofuels. So these are fuels that are generated from plant matter or produced by microorganisms. So these ones, you don't have to wait for the plant or the animal to decay over millions of years. The plant or animal is actually producing it on a much faster time scale, kind of almost like you're almost like farming fuels basically in some ways that you do it. So it's not necessarily going to be like totally carbon neutral, but it's a lot better because when you prepare the fuel using a living being, they take some of that CO2 that you would release from burning it and convert it back into a fuel. So it sort of reduces the overall net CO2 amount that's formed. And so there's a lot of liquid fuels that can be made in this way. Most of them are alcohols, methanol or ethanol. The gasoline we get today has a lot of ethanol in it already. And the nice thing about these is because they're liquids, we wouldn't have to totally redefine the transportation industry to use them. They work already reasonably well, at least in mixtures, with the current vehicles that we have. Another one that's you may have heard of before is called seed oil. So this is an oil that's produced by some plants that you can harvest and use as a fuel. All right, so again, the point of that was just to give you a little bit of sort of societal relevance to the things that we learned in chapter 7. And long story short, when you're talking about anything related to energy and fuels, either the generation of energy or the storage of energy, burning of fuels, all those things really are related to delta H, the amount of energy that's stored by those fuels, and then being able to release that energy and do work with it is kind of the whole idea. So any questions on that little overview? All right, so I encourage you to read that section of the textbook, but I'm pretty sure the level that I covered it here in these few slides is as deep as you need to go, so don't need to be a world expert on this stuff, but it is nice to sort of see the relevance. All right, so any last questions on enthalpy, chapter 7 stuff before we move on to chapter 8? All right, so this is end of chapter 7. All this stuff will be third exam, but in terms of how the homework assignments are organized, this is end of chapter 7. Now we're going to start with chapter 8 here. Okay, if you're following along at home. So what we're going to cover in the last two chapters of the book are the different states of matter that we have, solid, liquid, gas, and some, a lot of their key properties, a little bit about their, structural things, changes between them, converting liquids between, converting solid to liquid, liquid to gas, and so on. So all that stuff is going to come up in these last 2 chapters. So we'll have kind of a more complete picture of everything after we go through chapters 8 and 9. So we're actually going to start in chapter 8 with gas. We're going to go in the opposite order, gas, liquid, then solid. So this chapter will be all about gases. But let's talk briefly about the difference between them. All right, so here what we're showing is just all different phases of water. These little tiny molecules, if you can tell, are H2O. And so if you have solid water, which we call ice, so solids in general have a fixed volume and shape. Now some solids can be molded and stretched and things like that, but generally if you take a solid and you set it down on a table, it's just going to sit there. It's not going to start flowing or moving or diffusing throughout the room or anything like that. It's just going to sit there. It has a fixed volume and shape. And so at a molecular level, what that means is that the atoms or molecules that make up that solid are pretty much fixed in place. They can, vibrate around a little bit, but they're not moving all over the place. They're kind of stuck there. And in chapter 9, we'll talk about sort of how those atoms and molecules arrange themselves in different types of solids. We'll also talk about liquids in chapter 9, so that's not coming just yet. But the difference then with a liquid is that it has a fixed volume also. But the difference is that it conforms to the container shape. So, if you take, obviously, as you guys know, if you pour a liquid from one container to another, the shape of that liquid changes. If you have a really, shallow container, it's going to spread out and cover the whole surface of that container. And if you pour it into like a big long tube, it's going to then take on that shape. So it takes on the shape of whatever container it's in, even though the volume itself is constant. And what that kind of, the reason that happens is that it has an upper surface. So it doesn't just spread out in all directions. It does have sort of an upper surface that binds it together. We'll talk about why that is in chapter 9, but that's how liquids behave. So the molecules in liquids are moving around. They're sort of sliding all over each other, randomly tumbling around, but they don't just spread out everywhere. They're still kind of held together in some way. And then the ones we're going to talk about in chapter 8 are gases. And so these are substances that a state of matter that completely fills the container that it's in. They're freely flowing, so they can flow in all directions. There's no upper surface or any bounding surface to them. And they have low density. So compared to liquids and solids, as we'll, again, talk about a little bit quantitatively in this chapter, gases have densities that are probably 100 or 1,000 times smaller in most cases. So they're really low density. So if you have a gas, it's going to fill up the entire available volume that it has to it. So if I took a balloon and popped it at the front of the room, let's say I filled it with, I wouldn't do this to you guys, but let's say I filled it with a sulfide, which I think they use dimethyl sulfide or something like that. That's when you smell natural gas, that smell that kind of has that rotten egg smell, you're not smelling the natural gas itself, you're smelling a little additive that they put in it that your nose is extremely sensitive to, because natural gas itself is odorless. So I took that substance up here at the front of the room, and I had it in a balloon, and I popped it. Eventually, everybody in the room would be, running for cover because of that smell. So the gas will spread out over the whole room. It won't be instantaneous, but that does happen with gases. It'll spread out, fill the entire container that it's in, and there's no fixed volume to them. So that's because the molecules in gases are not really held together at all. They're zooming around, bouncing off each other, but not sticking together in any way. So again, that's going to be a topic that we'll dive into in detail towards the second half of this chapter. But the first thing we're going to talk about are different properties of gases. We've seen pressure a little bit in chapter 7 because we talked about expansion work, a gas expanding against constant pressure, and the value of the external pressure goes into that. So pressure, as we talked about, is defined as force divided by area. And so because gas molecules are constantly moving around and hitting, they're going to run into the wall of whatever container they're in, either the room or just the container if you have it in that way, and then that's going to push against the walls of that container and exert a pressure. Or similarly, your body feels gas pressure even though you don't realize it because gas molecules are constantly bombarding off of you and exerting a force. So that's what pressure refers to, and it's one of the key properties of gases we need to understand. We're going to talk first a little bit how to measure it. So if you want to measure atmospheric pressure, the pressure that the current atmosphere around you is exerting, we use what's called a barometer. You may have heard of barometric pressure in the context of weather. And a really low-tech device that you could use to do that looks like this. And so what you have is a plate of a liquid, usually mercury, and then you invert a tube in that. And so what happens then is that the gas pressure pushes down on the surface of the mercury that's in the dish and forces some of it up into the tube. And basically how high that column rises up is going to be related to the pressure that's being pushed down by the gas. And so this is how we would measure atmospheric pressure, the pressure of the gas that's sort of around us. And so here, the atmospheric pressure at sea level is approximately 760 millimeters of mercury. And so if you have atmospheric pressure pushing down on this dish, this simple barometer here, forcing up the mercury into a tube, that mercury is going to rise approximately 760 millimeters up the tube, which is about 3/4 of a meter, maybe a little bit more than 2 feet tall. So if I was on a table, it'd be like about this high. And so the reason we use mercury instead of water, you're like, well, mercury is dangerous, and why do we use that for barometers and not just put a dish of water out there? Well, the reason is because how high that column goes depends on the density of the liquid. Mercury is exceptionally dense, so you don't need a very tall column for it. If you wanted to make a water column as a barometer, you could do that, but 760 millimeters of mercury would correspond in height to about 34 feet of water. So you would need a barometer that's about 3 stories tall to be able to even measure atmospheric pressure. So that's not a very practical way of doing it. That's why we use a dense liquid like mercury in a barometer. Okay, so that's 700. So that's how we measure atmospheric pressure. And again, that's the key use of a barometer. So in terms of the terminology that's going to sometimes come up in homework questions and exams, if you see somewhere that we say the barometric pressure is so-and-so, that the barometric pressure then refers to the pressure of the atmosphere. That's what I mean by barometric pressure. Now the other pressure measuring device that we want to introduce you to a little bit is called a manometer. And this is the pressure of a gas sample. So if you have a closed container of a gas and you want to measure how much pressure is in there, you'd use a manometer. And again, there are digital, more technically complicated ones, but the simple way of doing this also involves tubes of mercury. The difference here is that you have sort of this U-shaped tube now. And so there's 2 types of these that we should be familiar with. So we're going to divide it up here. So the first one is called a closed-end manometer. So that's what this one is showing here. There should be better diagrams than these in your book if these ones are a little bit small for you. But basically in a closed-end manometer, you have this bulb here is your sample of gas that you're measuring. You have a U-shaped column of mercury here, and then above that mercury column it's totally closed off, and there's just sort of an evacuated, a vacuum here, no pressure above the mercury. And so then what happens is when you put gas into this bulb, it pushes down on the column of mercury over here, and that forces it up on the other side of the U. And you can basically just measure the difference between the height on the side of the gas and the height over here. And in this case, it's measured relative to vacuum. There is no opposing pressure coming down on the other side. And so what that means is that the difference in height between those 2 sides directly gives you the pressure. Vacuum has 1 C and 2 U's. Someday I'll remember that. So you're measuring the pressure relative to a vacuum, which means that this delta H, this difference here that I'm showing between the 2 sides of the mercury column, that distance is exactly equal to the pressure of the gas. As we said, you can measure the pressure of a gas in terms of the height of a mercury column in millimeters of mercury, and that's what that would give you. In an open-end manometer, which is shown over here, the design is similar, and the picture may not make this obvious, but the key difference is that this side of the tube, the one that's away from the gas, this is totally open now, so the atmosphere is pushing down on that side. And so in this case, what you're measuring is the pressure relative to the atmospheric pressure. So you have your gas over here in the bulb that's pushing down on the column of mercury over here, and then it's opposed on the other side by the pressure of the gas in the atmosphere pushing down. And so it's kind of a competition between those two. And so basically, this mercury column can be either higher on the side of the gas or higher on the side of the atmosphere, depending on which of those values is higher. And so when you measure this, the pressure of the gas is going to be the pressure of the atmosphere plus or minus delta H, the difference in height. So in this situation here, that's your delta H value between those two lines. If the mercury column is higher on the side of the gas, that means the gas is not pushing as hard as the atmosphere, which means that the gas pressure is lower than atmospheric by that amount. In this one over here, if the gas pressure is higher, it's going to push down harder on this side than the atmospheric pressure pushes down on the other side, and so the column will be arranged in this way, where it's higher on the side where the atmosphere is. So whichever side of the manometer the mercury column is higher, that's where you're going to have the lower pressure. So in this case, the gas pressure is higher than atmospheric pressure. So it can be plus or minus that difference in height. So in order to use a manometer like this, an open-end manometer, you also need to know the atmospheric pressure. So you'd measure that with a barometer, you'd measure the difference in height using this device, and the combination of those two gives you the pressure of the gas. So there will be problems like that in the homework assignment to get you a little bit used to those concepts, but it's just two different types of manometers in two slightly different ways of measuring it, but they give you the pressure of a sample of gas that's enclosed in usually a glass container like this. All right, any questions on that? Not the most important thing, but that's just a little bit of background of how we measure things. All right, now what we do need to be very familiar with, though, are the different units of pressure that we have. So if we were strictly using SI units, the standard system international units, the French term that I'm not going to try to pronounce in French, but that's what SI stands for, that is going to be called a Pascal. And so 1 Pascal, remember, pressure is force divided by area. So the SI unit for force is newtons, which you probably use all the time in physics class. And then the SI unit for area would be square meters. So 1 Pascal is 1 Newton per meter square. That's the SI unit for pressure. So again, N is a Newton, which, if you break it down further into SI units, is kilogram meters per second squared. So that's kind of the more physics level definition. So while that is the SI unit for pressure, it's not a particularly practical one because it actually represents a very tiny pressure interval. So we don't use pascals a lot, especially in a chemistry context. The most common one that we use in chemistry is called the atmosphere, abbreviated as ATM. And so 1 atmosphere represents the average barometric pressure at sea level. So again, atmospheric or barometric pressure mean the same thing. It's measured with a barometer. So the average barometric pressure at sea level over all the world is defined as 1 atmosphere of pressure. And so we can report then the value of any other pressure relative to that, where that's sort of our unit of measure is 1 atmosphere, the pressure at sea level. And in terms of how that relates to SI units, and again, the reason we use atmospheres more than pascals is that 1 atmosphere is 101.3 kilopascals. So there's a lot of pascals in 1 atmosphere, which is 1.013 times 10 to the 5th. And so a related unit that you might see from time to time, although we don't use it a lot in this course, is we define 10 to the 5th pascals as 1 bar. So this is also equal to 1.013 bar. So bar is a pressure unit that's very similar to atmospheres and is based more strictly on the SI unit Pascal. But again, we're not going to see bar a lot, but they're pretty much the same as 1.01 bar per atmosphere. So that's the relationship between those. The more common relationship you need to be understanding in terms of pressure units is the one that involves this unit called torr, which is short for Torricelli, named after an Italian scientist. So 1 torr is equal to 1 millimeter of mercury. So when we measure gas pressure with a mercury manometer or barometer, we directly measure the height of that column, and we can just report that then as a pressure unit, which is called millimeters of mercury or torr. Those two things are numerically equivalent. So these are used interchangeably. They're exactly the same numerically. Don't know why we have both, but we do. All right, so they're used interchangeably, but the most important conversion factor for you guys is going to be the relationship between torr, millimeter of mercury, and atmosphere. So 760 torr or 760 millimeters of mercury, those are the same, is equal to 1 atmosphere. Okay, so that's the conversion factor you should be the most familiar with in this course, which you'll use a lot in the different problems that we do. Okay, so that's going to be the units of pressure, atmosphere and torr being the two big ones, or millimeters of mercury, which is the same as torr. All right, so let's just do one example of how to convert units of pressure. So if you have a compressed gas cylinder, like the type that you would use to inflate helium balloons, although I encourage you not to, because helium is starting to get scarce now. We have much more important things than balloons, unfortunately. But compressed gas cylinders are usually supplied at 2,000 psi. So psi is another pressure unit based on the English system, which means it's functionally useless in the context of chemistry, but it is out there a lot if you're in the sort of engineering world especially. So 2,000 psi is pounds per square inch. That's what psi refers to. So again, it's a force divided by an area. But that's the unit that we use a lot in the United States, especially for things that are supplied commercially. So you have a 2,000 psi, or you know that if you have to inflate your car tires, that number that you go to, 30, 34, whatever, that's also in psi. That's the unit that we use a lot of times. But a gas cylinder is 2,000 psi. If we want to know what is the pressure in millimeters of mercury, so it's just going to be a series of conversions. We gave you the one here. This one you wouldn't have to know, so we gave it to you. This one here you should know, the 760 torr, 1 per atmosphere. So it's just unit conversions. We have to refamiliarize ourselves with that because it's going to come up from time to time. So we have 2,000 psi. We have a conversion to atmospheres first. So 1 atmosphere is 14.7 psi. And then once we're in atmospheres, we can go to 760 torr in 1 atmosphere. And then, as we said, this is a trivial one. We didn't have to do it as a separate step. Millimeter of mercury and torr are the same thing numerically. So that set of conversions, the last one being sort of not necessary really, gives us 1.03 times 10 to the 5th millimeters of mercury, which is what we asked for, but if you want to know what that is in more common unit, meters is 100 meters. So 100 meters is like 300 feet tall. So clearly if we're measuring really high pressures, we don't use mercury columns to do that. We're not going to make a 10-story tall, and this would be 300, it's like a 30-story tall mercury column to measure this amount of pressure. We're not going to do that. So there are other ways of measuring high pressures, but anyway, this was just a unit conversion problem, so you don't need to worry about that. All right, any questions on pressure or pressure units? Now the key thing we're going to do, oh sorry, yeah, go ahead.
Will we always be given when ATM is equal to 14.7?
Yeah, that one you wouldn't have to memorize. Anything that's like a non-standard, English unit, you wouldn't have to memorize. All right, any other questions? All right, so then the key thing we're going to do in the first half of the chapter. So chapter 8 is kind of divided into 2 major sections. I mean, it has more sections than that, of course, as in the textbook, but really 2 major themes. The first is going to be, sort of at a macroscopic level. We have different properties of gases. Pressure that we just talked about, volume, how much space it takes up, temperature, we know what temperature is, and then the number of moles of gas, how much gas we have. All those 4 different things, we're going to talk about relationships between them. And then in the second half of the chapter, we'll talk about sort of at a microscopic level what's happening with atoms and molecules that are in the gas phase and how that relates to some of those relationships and properties. So we're going to go through the different relationships between these, and they're all going to be based on the response of volume to other different parameters. The reason we do it, these were sort of how they were sort of developed historically, and the reason it was done in terms of volume is because volume is very easy to measure. How much space does the gas take up? You could do it in a balloon even. It's a pretty low-tech way of measuring the volume of a gas. So we're talking about relationships between volume and all different things. So the first one we're going to talk about is the relationship between volume and pressure. And so before I get into the mathematical parts of it, let's watch a video to see what happens when we change the pressure of a gas. How does the volume of that gas respond? Okay, so we have a video queued up here. I was actually on top of things today and have it ready to go. So what we're going to be doing in this video, is it going to start automatically? Yes, let's pause it for a second. This relationship is called Boyle's law, the relationship between volume and pressure. And what we're going to be doing in this video is we're going to have a balloon that's filled with gas initially, and it's going to be at regular atmospheric pressure, and then they're going to put it in a vacuum chamber that lowers the pressure of the surroundings. Basically going to pull all the air out of that chamber so that the pressure inside of there drops, and we're going to see what happens to the volume of the balloon. Okay. Eventually it'll start. Okay, so there's our balloon, and this is hooked up to this little tube here, which is a vacuum tube. And now you can see as they pull vacuum on that chamber, the balloon gets bigger and bigger and bigger. So as the pressure inside of there goes down, the volume of the balloon increases. That's what you'd call an inverse relationship between pressure and volume. Pressure goes down, volume goes up, and then eventually it's going to fill the container and warp in all these different ways. Amazingly, it doesn't pop. And then when they put the air pressure back in, when they release the vacuum and allow it to repressurize, the volume goes back down. So it's totally reversible. Now, you don't have to do this with balloons. You can also do this with marshmallow peeps because they have a lot of gas trapped inside of them as well. So if we pull vacuum on a marshmallow peep, let's see what happens there. I think you might imagine what happens. And so there it goes. It's growing. And unfortunately, the structural integrity of this is not perfect, but it does go back pretty well, but eventually it kind of collapses on itself. So poor guy. Easter is coming up, so I guess that was timely. All right, and then we're going to do it with shaving cream. Shaving creams also have a lot of gas trapped inside of them. You pull vacuum, the pressure gets lower, the volume expands of those gases, and you can see that the whole thing expands and fills the container. Okay, so the whole point of this is that there's an inverse relationship between pressure and volume. As the pressure was reduced in this case, we saw the volume get bigger. And that's called an inverse relationship. Okay, so let's get out of here. Let's close it because otherwise it'll autoplay something. I don't want to find out what that is. All right, so that's what's called Boyle's law. It's an inverse relationship between pressure and volume. So that means volume is proportional to 1 over the pressure, or vice versa. And so the way we read that is V, volume, is inversely proportional to P, pressure. Now, as we talked about already in the last chapter, and at least maybe one time before that, if you want to get rid of this proportionality sign and turn it into an equal sign, you have to put a constant on one side. Now for Boyle's law, we don't really do it that way though. We can. I mean, we can say that the volume is equal to some constant K divided by the pressure P, but this constant is not a universal or well-defined constant because it depends on, as we'll see later on, how much gas we have, and it also depends on the temperature. So it's not going to be a fixed value for every situation. So it's not a very useful way to do it. But what you can do then is you can rearrange this, cross multiply, and say that pressure times volume is equal to a constant K. And so because the pressure and the volume multiplied together are always equal to some constant value, as long as everything else is fixed, the temperature has to remain constant, and the container volume, or the container has to be closed, that gas is not escaping or being added at the same time. So as long as that situation is true, this product, P times V, is equal to constant, which means that if we're changing the pressure and the volume, the product of the pressure and volume before and after have to be equal to one another. And so the way that we would usually write this relationship then is as P1V1 equals P2V2. It looks a lot like the dilution equation, just pressure and volume instead of molarity and volume. Okay, so if you have a gas and it's at a constant temperature and it's just a sample of gas that's not changing in terms of the amount that you have, the pressure times the volume is constant, so P1V1 equals P2V2. So that's called Boyle's law. So we are going to have today 3 different individual gas laws that we come up with that all look kind of have similar mathematical forms to this in some way or another. It's sort of useful to know them and kind of understand them individually at some level, but as we'll see next time, there's really one unifying equation that would give us all the relationships we need for a gas. So you don't necessarily have to use these individual equations all the time, but we'll get to that eventually. But let's just talk about Boyle's law first. So here's an example of it. All right, so if you have a balloon at sea level inflated to 0.5 liters, and so if it's at sea level, that means the initial pressure is 1 atmosphere, even though that's not stated here. And then you let that go. Again, not great for the environment, so I would not recommend this practice all the time. And then the balloon rises to an altitude of 6.5 kilometers. So before the Biden administration shoots it down, sorry, I should not have said that. It gets to an altitude of 6.5 kilometers where the pressure is 0.4 atmospheres. So what will the final volume of that balloon be once it raises up to that level where the pressure is now dropped to 0.4? So this is classic Boyle's law. We're assuming the temperature is the same at the higher altitude, which is probably a bad assumption, but that's what we have to do here. And we're just going to say, okay, how does the volume change? So we're going to use that Boyle's law relationship. P1 V1 equals P2 V2. All right, so that's going to be the relationship, the mathematical relationship, and again, we just have to solve for what we're looking for. So we're looking for the final volume, so we'll call that V2, which is going to be P1 V1 over P2. All right, so what we're told is that the initial volume V1 is 0.5 liters. We're at sea level, which tells us that we can assume that the initial pressure is 1 atmosphere. It may not be exactly that, but it's close enough. And then here, this is our P2, final pressure that we go to. So we just have to plug everything in. We have P1 is 1 atmosphere. For problems like this, with pressure and volume, the units that you use are sort of up to you as long as you're consistent. So it's going to be 0.5 liters is V1, and then the only important thing is that the two pressure values that you use have the same unit. So they don't have to be in any specific one. They don't have to be atmospheres. They don't have to be millimeters of mercury. They just have to be the same on the top and bottom. So we're using atmospheres on the top, so we'll keep it at 0.4 atmospheres on the bottom. That will ensure that the pressure units cancel out, and that gives us an answer in liters. So when we multiply this across, we get an answer of 1.25 liters. So the balloon volume has increased from half a liter to 1.25, so more than doubles. So if it doesn't pop at that level, as long as the material is strong enough to keep that volume, that's what would happen as it raises up. All right, any questions on that? All right, pretty straightforward stuff so far. Let's go to the other one now, the next gas law, which is called Charles's law. And this is where we have now a constant pressure. So we're keeping the pressure the same, still a closed container, so we're not adding or subtracting gas molecules from the system. And we're going to look at what happens to the volume as a function of temperature. So we're going to change the temperature of the gas and see how the volume responds. Now I'd like to point out chemical safety from time to time when these videos come up. This person makes the inspiring decision to work with liquid nitrogen with no protection on their hands. Not my recommendation for you guys. You can get cryogenic burns from this. So apparently they come out of it unscathed, but it's not good practice to just play with liquid nitrogen with your bare hands. So that's what he's doing. He's gonna have a balloon filled with air, and he's gonna dunk it in liquid nitrogen to cool it down rapidly and see what happens to the volume. So again, should be wearing some sort of protection on his hands, and they look fairly masculine. I shouldn't assume that it's a man's hands, but whoever's doing this, they're not being very safe about it. But you can see that the balloon volume shrinks down to basically nothing as it gets colder and colder. The gas inside the balloon shrinks to a smaller and smaller volume as it gets really cold. And then when he pulls it out, and lets it warm up, you can see that the balloon restores to its original volume. So that's a demonstration then of what happens when you have, I guess that's the same experiment, different way. But again, I'm not going to let autoplay go because I don't like that uncertainty of what's coming up next on YouTube. All right, so for Charles's law, that's the relationship between volume and temperature. And we saw in this case that those two were directly proportional to each other. When the temperature got lower, the volume got smaller. When they warmed it back up to a higher temperature, the volume got bigger again. So that's a direct relationship, meaning that volume and temperature are directly proportional. Written like that, or stated as V is directly proportional V is directly proportional to T, which means that if we want to get rid of the proportionality sign, we have to write a constant on the other side. I'll call it K prime just to not make you think that it's the same constant that we had in the previous problem, because it won't be. And again, this constant depends on the pressure of the system. It depends on how many moles of gas we have. So it's not a very useful constant because it's not uniform across all situations. But what we can do is we can say that the volume over the temperature, divide both sides by T, is equal to that constant. meaning that V1 over T1 equals V2 over T2. So this would be the most useful mathematical form of Charles's law, the relationship between volume and temperature. Now, as I'm sort of hinting at already, you don't necessarily need to memorize all three equations, because there's going to be one unified gas equation that we'll get to next time that allows you to establish all of these relationships from the same starting point. But if you want to know them individually, that's fine too. And this is the relationship between volume and temperature if everything else, pressure, number of moles, is constant. Now that we've introduced temperature, though, into the story, we have to be careful with units for temperature especially. So volume can be whatever units you want, as long as they're the same on both sides. In the previous problem, we had pressure units. Those can be the same. They can be whatever you want as long as they're the same. But when we're using temperature, just T, not delta T, but just absolute temperature, T, it must be in the units of Kelvin. So anytime you're doing a gas law problem that involves temperature, get used to putting your temperature in Kelvin units. And as a reminder, the way that we do that, because we usually use Celsius more often, is you take the temperature that's in Celsius and add 273. Technically 0.15. If you just did 273, it'd be close enough. We're not going to be that precise on exams. But nonetheless, you have to make sure you convert into Kelvin whenever you're going to use temperature, anything related to the gas laws that we're going to be covering in this chapter. All right, so if you see, this sometimes causes some confusion, so let's get on top of it. Chapter 7, we had delta T all the time, change in temperature when we're calculating heat. In that case, you could be Celsius or Kelvin because the difference between those two is the same in either unit. But here we're doing absolute temperature, no delta in front of it, just temperature by itself. It has to be in Kelvin, so just get used to doing that. Okay, so that's Charles's law. Let's just do a quick example of that. And this will get us used to those temperature units also. So we have a sample of gas that has a volume of 79.5 milliliters at 45 degrees Celsius. What would it occupy at 0 degrees Celsius if the pressure were held constant? So again, this is relationship between volume and temperature. As we just introduced, V1 over T1 equals V2 over T2. They're directly proportional. All right, so that's Charles's law, and we're looking again for the final volume after we change the temperature. So V2, which is going to be V1 times T2 divided by T1. So we have to plug things in. But as we said, when we're using temperature, they need to be in the correct units. So we're given everything else. We're given everything we need here. This is our initial volume V1. This is our initial temperature T1, and this is our final temperature T2. So all three of those things we have, but they have to be in the right units. So volume can be whatever we want. There's no restriction on volume units. We have to keep track of what they are. So if we put it in directly as milliliters, that's fine. But the two temperatures need to be converted into Kelvin. So the first temperature in Kelvin, T1, is 45 degrees Celsius. We add 273 to that, or 273.15 if you're a really real stickler for exactness. But anyway, 318 Kelvin, close enough. And then the second temperature, T2, was 0 degrees Celsius, the temperature of freezing water. We have to add 273 to that, so that comes out to 273. And so what we put in for the two temperatures, our T2 is 273 in terms of Kelvin, T1 is 318. And so that comes out to 68.2 milliliters. So not a huge change. It goes from 79.5 to 68.2. And that's because in terms of absolute temperature, that's not a huge difference. 0 degrees Celsius to 45 degrees Celsius, that sounds like a pretty big jump. I mean, 45 would be like the hottest day we ever had in Houston. That's about 40 is like 104, so 45 would be like 113, I think, Fahrenheit. Not a temperature we would like to get to very often, but we probably have in our lifetime. So that's 113 Fahrenheit, and then 0 degrees Celsius is 32 Fahrenheit, which is basically about as cold as we usually get in Houston. So that's a big difference in terms of what we feel, but in terms of absolute temperature, it's actually kind of small, 273 to 318, so there's not a huge effect on the volume. So you have to get used to using Kelvin as your temperature unit for all these types of problems. That's going to be important as we go through a lot of different things in this chapter. All right, any question on Charles's law? Okay, so the last thing we're going to cover today is Avogadro's law. And this one I don't have a video for, but I think it's very intuitive. And And this is going to be the relationship between volume and number of moles. The abbreviation we're going to use in the gas law sections is N is going to represent the number of moles. Okay? So this is actually what Avogadro is known for, as it turns out. The number was just kind of named after him as a tribute, but this is what he's actually known for, this relationship involving volume and number of moles. And I think this one should not be too hard for us to think about. So if you have a balloon, I mean, the picture gives it away, but just, close your eyes and think about it if you don't want to look at if you don't want the picture to lead you on. If you have a balloon filled with 1 mole of gas and you pump in another mole of gas, is the balloon going to get bigger or smaller? Bigger. Yeah, it's not a trick question. So that's exactly what happens. The volume gets bigger as you add more moles of gas to the sample, all else being the same, meaning the pressure stays the same, temperature stays the same. And so what that means is volume and number of moles are also directly proportional to each other. The more moles of gas you have, the bigger volume it will occupy at constant pressure and temperature. And so again, we can write this as an equality with the constant, I'll call it K double prime, again, not implying any sort of relationship between these constants that are ill-defined, but the more useful way is to move everything over. Volume divided by number of moles is equal to a constant, and that means if we're changing those, V1 over N1 will equal V2 over N2. All right, the one thing to be careful about with how we set up some of these problems is that N here, the number of moles, is the total number of moles of gas you have. It's not how, N2 would not be the amount that you're adding to the system, it would be the total that you have at the end. Kind of like when we do dilution problems, V2 is the final volume, not the volume that you add. So you have to make sure that we keep that straight for some of these. But that's the relationship. Again, looks very similar to the last one, just number of moles instead of temperature in the denominator. So if we do a quick sample problem on that to close up today, if we have, at a certain temperature and pressure, we have 28 grams of nitrogen, N2, which has a molar mass of 28, and that occupies 20.8 liters. How much volume does 40.0 grams of O2 occupy at the same temperature and pressure? So this problem teaches us a couple of important things. First of all, it reminds us how to convert mass into moles, which we're probably sick of by now. But the other important thing about this problem is that it shows us that it doesn't matter which gas we're talking about. Every gas, we'll talk more about what it means to be an ideal gas, but that's a technicality for later. But every gas is going to follow these relationships. And it doesn't matter for these types of problems what gas you're talking about. You just need to know pressure, volume, number of moles, and temperature. Those 4 things tell you everything you need to know about the gas. It doesn't matter what gas it is. So here, even though we're comparing 2 different gases, this relationship V1 over N1 equals V2 over N2 is still going to apply to that situation. Even though the two numbers, the 2 gases we're comparing, different numbers of moles, also different gases, but all that matters is how many moles of each we have, not what they are. The reason that what they are matters is because that's how we're going to calculate the number of moles, but what they are doesn't affect this relationship involving volume and number of moles or any other relationship that would come out of this. Okay, so we have to find the 2 things. We're looking again for the final volume. So if we call this V1, and then this is going to give us N1 eventually, and then our final volume is what we're looking for, V2. We solve for that. It's going to be V1 times N2 over N1. All right, and so we're going to start plugging things in. So the initial volume, the volume of the nitrogen sample is 20.8 liters. And then we just need the 2 numbers of moles of gas. So N1 is going to be the number of moles that corresponds to nitrogen, because nitrogen occupies the given volume V1. So N1 is going to be the number of moles of nitrogen, and it's just a mass to mole conversion. We don't use masses a lot with gases, as it turns out, but the relationships are still true. So if we have 28 grams of nitrogen, this one we can do in our head because the molar mass of nitrogen is also 28. And so that gives us exactly 1 mole of N2. So that's our initial number of moles N1, which corresponds to our initial volume V1. And then N2 is going to be the number of moles of oxygen we have in the other sample that we're comparing it to, which has a mass of 40 grams stated in the problem. Molar mass of oxygen is 32, also given to us here. And so that comes out to 1.25 moles. All right, so that's how we calculate them, and they're different from each other, so they should occupy different volumes by Avogadro's law. But again, we don't care that one of them is nitrogen, one of them is oxygen. The relationship between volume and number of moles holds for any gas that we would consider. So N2 is the number of moles of oxygen. N1 is the number of moles of nitrogen that we're comparing it to. And that multiplies out to give us 26.0 liters. So more moles of oxygen should occupy a bigger volume, which it does. All right, so that one is called Avogadro's law. So what we're going to get to next time, and I didn't want to try to rush through it today, so we'll put it off till next week, is putting all three of these gas laws together. So we have individual relationships, and it is useful and helpful to understand them and appreciate them, and this is kind of historically how things were developed. They developed them one at a time, the effective volume on different things. But what we're going to do next time is put all three in together into one combined gas equation, and that's going to be really the starting point for a lot of the gas law problems we do, where we can still derive these same relationships from that, or we can also derive other relationships that involve more than two of the variables, or different ones, different combinations that we had here. So that's going to all come next time, and I'll see you guys then. Again, if you have anything you want to go over about the recent exam, try to come find me, and I'd be happy to go over it with you.